the video going? The video's working. But you can't hear this. So you can hear this. When you said is the video on? Hello? But you can't hear this, I can hear that now. So you can hear what I'm saying now? Only through the mic. I can't hear anything else. So do I have to stand really close to it? Can you pick it up? Can the speaker pick it up? Yeah, but it's only, she can't really move very far from the...
Why not the other mics? Oh, it's connected.
Can we connect? Hello? Wow, there's a serious delay in this. So you can hear what I'm saying.
It is a big delay. Oh, you already got water for it.
Can we somehow connect the Toby?
Yeah.
Can we somehow...
Do I have to stand really close to it?
Can we somehow...
Oh, what was that? That's when you detach the mic.
Oh.
Yeah, but she can't really move very far. Okay, I'll turn that down.
Why not the other mics? Oh, gee.
Here.
I can.
Well, through the live stream, I'm just waiting.
Okay.
You can probably hear it. Because when I was talking, I didn't hear myself.
Oh, okay. It should be okay then. Maybe turn the microphone back up again.
Is that better?
Can you hear me now?
There's a big delay.
Okay.
It's just a question for a while.
Emily, do you want to speak?
Also, if you move back on the live stream and see if you can hear us?
I'm currently on the live stream, so...
Okay, I'll just speak. And then let me know.
Use that speaker because that's the most important bit.
So will she have it like on her?
Yeah.
So I'll just like have it there.
Yes, but with the actual microphone.
So it'd be like here?
Roughly.
Here. Okay, so I'm speaking now.
Also, not that there's a delay, so it takes a while. It's really, really quiet, so I might turn up the volume on the audio on the screen as well.
Okay, I'm just gonna keep on talking.
Yeah, but we haven't messed around with seven. When you asked me if I could go on the live stream, that was loudish, but you were shouting, so...
You want to try talking into the microphones now, guys?
Okay, I'm talking into the microphone now.
Awesome. Okay.
Also, can we get the PowerPoint up? Yeah. Oh, okay, hello. Just send that.
Okay, I think that's all right now, isn't it? Yeah, that was really loud. I could hear that. Okay, over here.
It's quite loud now, I think.
What, out of the speakers?
As in, I can hear myself talk. So it's...
I mean,
It should be good.
that's loud. Like, what's your what volume is your phone on as well? 'Cause
Max
yours-
volume.
That's max. So if that's
okay.
max, that's pretty decent.
Yeah, that's all right.
It's fine.
That's good. That's good. So
So
now
it's not
we need to get the PowerPoint up.
And I feel like-
But she had it. She has it on her computer,
She
right?
has on her computer.
Oh, great, okay.
So we'll have to set everything up again on her laptop.
Right, lighting there.
Okay, I'll stand in the drinks room. Oh, yeah, that is mine. That's mine, isn't it?
Yeah.
That's a decent level for the talk, right? And if she wants to show something, like it could get darker, but I feel like 3 is a decent level.
Yeah, no, I think the previous thing was better.
Yeah.
Because otherwise it becomes a bit too dim.
Level for the talk, like, yeah.
Yeah.
Yeah, you reckon that's a good light level? I'd say that's okay.
I think that's good, yeah. Also, I think you can put a like spotlight on. Actually,
Ah, the spotlight, yeah, I remember that. How do you set that one up?
that one's not on the like free, that's on the actual dials.
It's on the dial.
Yeah.
What? I know, they give us loads of quizzes with no crackers. Like, how many was that? 3 crackers.
Any normal person would look at them on the cheese and think, that is not the right amount of quiz.
No, because no one eats the quiz. Everyone eats the cheese and crackers. You bet they can charge you. I bet they're going to charge us so much, like,
Yeah.
they're going to charge us like 5 like 20 quid. Literally is.
Wanna check it?
It's so
Well,
Yeah, no, it's ridiculous. And they'll charge us for that. Yeah, I kept on saying that, oh, I'll email them. Oh!
How bad was it?
It was just funny.
So like you couldn't hear it being like, oh, there's so much quiz.
I think we might have actually done that.
Oh no.
Where's the...
Anyway, how expensive do you think the wine will be this time? Because the label says 2007. Is that that good or bad? I don't know why. Like that's older than the last 2 years, so maybe.
Maybe they give us a really expensive wine.
Maybe.
Well, I didn't ask for
Do
it.
they charge different prices for the wine? It could be that they just had some wine to get rid of. Maybe. But still.
She did her bachelor's in Chile and did her PhD in Geneva. Well, she started off as she also very slowly doing various things like one of her today is talking about the discoveries made in James and what we learned. So once again, as usual, unless and then afterwards we all go to the living room where we'll have more things to discuss.
What are you studying? Hello, I have brought the people.
I am the people.
Yes. Is that water?
Okay, that's not my laptop.
Yeah, that, we were just testing it out.
Where are my stuff?
So much food.
It was my first one ever. There's so much food, and they ran a gun like twice, and we had to leave it lie.
Yes, the people stood up in respect.
I keep finding naughty stuff, and they end up being weird. Like yesterday, I was at this military base, and then suddenly, like everyone went quiet because the national anthem was playing. And if you make a noise during the national anthem, like you get kicked out.
Oh, really?
Yeah, and everyone would just stop everywhere, like on the street. They were like.
On hindsight, we actually get chairs. Plus, the rest of the whole museum selling it's because we get benches. Oh! Yes, you know, I have a conflict because I'm second year halfway through my degree, and the chair almost fell over behind. And throughout the whole thing, I had to stand like this.
Oh no. So when I signed up for dinner, like I didn't choose students because I thought that I would make people uncomfortable. Because I knew nothing about colleges, and then I let people know, and they were like, Charlotte, you know that you're going to have to sit on the high table. That's kind of funny. I didn't think about it. Yeah. The fun was really nice, so it was good.
Is that water?
Yes, that's for you, maybe first position.
Yeah, maybe. Yeah, I can wave my hands out. Is there somewhere I
So
can
there
put this?
should be a charger here. You should be able to plug this in to charge, and then ideally.
Yeah, you can plug it the other side. Okay, I'll go check on the people. Is the YouTube thing already on? Because my mom sent me a message saying that, oh, we can hear you.
Oh,
And I was in the bathroom. Like, I wasn't there. So.
Usually when we're testing, we have to kind of start the live stream to actually see anything. So it's a bit annoying because that means that technically it starts a bit earlier whilst we're still testing.
Yeah.
Normally that's not an issue because usually people don't join particularly early, but yeah, it was on a bit early.
Okay, but that makes sense. She's like, yes, we can hear you. Like, but I'm peeing. You can't hear me.
Are you sure you're not talking about in the future? Yeah, so I think the only things we'll need is just going onto YouTube and then I'll have to log into my account. And other than that, just have your presentation up.
Okay.
And I'm not sure what to do about, there's no...
About pointers? I can just do it.
Okay, and this thing...
What is that? Is that for mouse? Is that plugged in?
Because I think this thing is important streaming.
Yeah, but if I can plug in my mouse and then I can just use my mouse to...
I don't think this is a mouse.
Well, it's not, but I have a mouse that I can
Okay,
plug
if you
in.
have a mouse, then yeah. Get like a D&D campaign once you're like a postdoc?
Well, I haven't done it, but apparently people are really interested. So you're into D&D as well?
Yeah, I don't have a campaign really, but I've joined the kind of university society.
We want to do a D&D thing when my husband comes with some people from uni, because he's a dungeon master. I have already put So she's a wild magic barbarian. So every time she rages, the magic effect comes up. But she was a lich originally, so she was a mage, but she forgot everything because she was in a cave, and now she's just a barbarian.
That sounds really fun because I'm really chaotic.
Oh yeah, she's got a cow and she's got all sorts of stuff. Yeah, okay, so this is fine.
Can we bring up the YouTube then?
Oh, I need internet connection, right?
Yes.
I don't think.
Do you have a drone? Because there should be a drone here.
It wasn't working on my computer.
Okay, I want to see if I can figure out how to connect it to P-Trans.
Yeah, it never works. I'll try it again, but...
Could you try this code for P-Trans one?
Oh, yeah. Which one? Oh, god damn it. So bad. Okay, I think it's... Yeah, it's working. So what do you have to do?
So I'll log into my account.
No, my mom's saying that she saw me wearing a cape
Oh yeah, she.
She must have seen someone else.
Yeah. Wait, did you come in with a cape?
No!
Oh. Oh, I have to remember the password. You can borrow someone else's gown.
I wanted to, so I asked in my group, and I was gonna get one, but then this morning I wasn't feeling really well and I didn't go to the institute. So I did my best.
Yeah, it looks reasonably.
Yeah, as long as you don't look at my feet, it's all good.
No, just turn it.
Is it working?
Yeah, just Google requires me to like do authentication for me. Yes, that's me.
Oh yeah. That's really the English
Okay, so I think we can. The streamer should now be able to see you and
Okay.
your
So
PowerPoint.
if I start the slide, will
You
that
have a
work?
slide. They should.
So start from first slide.
And I'll.
Would that be? Oh, I can just ask.
Oh yeah.
They're writing.
Okay, I'll start bringing people over soon. If you're
Oh,
ready.
okay.
Or
Yes,
if you want-
I just want to make sure that people can see my slides.
Oh, yeah, and this is the audio device.
Oh! How does this work?
So essentially, it should already be on. So essentially, just
Okay, they
have
can
that
see the
in some
slides.
pocket, and then put this onto like a jacket.
It's already on.
Yes.
Women clothes.
Yeah, don't have a lot of
No,
pockets
we
usually.
don't have that luxury because we're women.
Which is so stupid. Like I'd expect capitalism to have fixed that, but not fixed it. That's it's the problem. But I'd imagine like I thought that like there'd be enough pressure by now
No.
for
No.
clothing to actually adapt.
Okay, so where should I just like hang it
I
here?
think on your jacket, kind of close. Would be,
Is that?
slightly higher up, I think would be closer to your voice. Yeah. we can-
Wait, my
hopefully
button?
work. We made sure that it's a bit louder, so then if people need to turn it down, then it should be fine.
Okay.
At least it shouldn't be too quiet. Hopefully.
Thank you.
Yeah, just let me know when you're ready. Already?
Yeah.
Hello.
Hey, the audience gets to drink. That makes my talk better. Well, that just makes my talk better. So.
Also, would you prefer to ask questions during the talk or at the end of the talk?
Whenever is fine. Okay. Yeah.
Okay.
Yeah,
hello. Okay. Anyways, hello. Welcome to the second Calvin Club talk of a term. Today we've got Dr. Charlotte Simmonds, who's doing her postdoc at the Calvin Institute of Cosmology. She did her undergraduate in Chile, and later on did her PhD in Geneva. And then, but before that, actually started off as a high school music teacher, later transitioning into research. She also has various fun hobbies like D&D in her free time. And today she'll be telling us about how we can use JWST to explore the very early universe. As usual, at the very end of the talk, we'll be able to go to the another room, and there we can continue to have more refreshments and potentially ask Dr. Charlotte more questions. Charlotte has asked that people are free to ask questions either during the talk or at the end of the talk, so feel free to raise your hand whenever. Yeah, so I leave the stage to you.
Thank you, Sebastian, for that introduction. Hi, everyone. I'm Charlotte, as he said. Thank you so much for the invitation. Thank you for the lovely dinner. It was so big. I'm so impressed. And thank you just for the very warm reception I've had. I look forward to meeting everyone else I didn't meet afterward for some drinks, if that's okay. So my talk, as you already know, is about JWST and the mysteries of the early universe. So when I say JWST, just so we all know what I'm talking about, it's a James Webb Space Telescope, and it's this little guy over here that's in space for about a year now. It's been floating around in space. As Sebastian said, feel free to ask me questions. I like doing outreach, so this talk is made for everyone to understand. And also, if you count the amount of cats that appear in this talk, you get a reward at the end. So a bit of context of why we're interested in the universe for everyone to be on the same page. So this is a schematic of the universe and how it has evolved in time. So we started with the Big Bang, which most of us saw in school in one way or another. I don't know what happened before the Big Bang. It's not my area. And it's a bit of a mystery, so I'm not going to touch it. But after the Big Bang, the universe was really hot, and it was a really hot plasma. So nothing could really happen. No atoms could combine because the electrons and the protons, everything was just crashing around. And so no light could pass through this because it was such a dense soup, as it's sometimes called. But eventually, I can't really point, but hopefully you know where I'm pointing. The universe, when it started with its expansion, it expanded enough that it cooled down enough that atoms could form. So protons and electrons and neutrons could form hydrogen. And then the universe started being transparent to radiation. This means that the light could finally pass through because we didn't have all this soup of particles just crashing around, which was great. The only problem was that we didn't have any sources of light. So this is when the universe started dark ages, what we call them. Because there were no stars, there were no galaxies, there was no source of light, it was just darkness. However, at some point, when enough time has passed, you start seeing that the first stars and the first galaxies started forming until we get the universe that we see today. And so in this talk, I'm going to guide you a little bit through what the JWST is as an instrument. Why do we care? We care basically because it's the newest, shiniest toy we have in space. And we are going to be interested, although the talk is about early universe, which means on this side, so the further away we look in space, we're also looking back in time. So I'm interested in the early galaxies, and that's actually what I work on in my research. However, we can also look at the nearby galaxies and stars to understand what is happening on the earlier galaxies. So I'm going to go through some very pretty pictures because we have to show pretty pictures when we talk about JWST, and then we're going to go into the early universe, which is a bit more like blobs than pretty pictures. So let's go. So as brief just overview, as I just said, we will first go through what JWST is. Then we will look at our beautiful backyard, so everything that's very close by, and it's so beautiful. It's all these pictures you keep on seeing on the news, and they're wonderful. And we can learn from them. They're not just pretty, we can learn from them. But they're also really pretty. And then the early universe, and also a bit of drama about the early universe. Stay tuned for the gossip. So the James Webb is a space telescope, which means it was built on Earth, but then we launched it into space. It was launched in Christmas 2021, cost $10 billion, and it's orbiting around the sun. So much like the planets, the James Webb is also orbiting the sun. And it has this big mirror that's coated in gold, that's 6.5 meters diameter. And it is supposed to last for 10 years. Which I think a lot of us are hopeful it's going to be more than 10 years, because the Hubble telescope that was here before was supposed to be about 10 years, and it's already been working for 30. So fingers crossed. So what was really cool about this, I'm going to show you an animation that it's going to look really pixelated, so it's in space. So keep that in mind. So once it was launched all together like a dead spider, right? Because you have to put it into space. But then it had to assemble itself. It had to open up its mirror. It had to open up this sun shield over here because we need to keep it cool and we don't want the sun to heat our telescope. So this thing that's being opened here is just a sun shield. So it's just to keep it cool. And it's about the size of a tennis court. So it's a huge project that was finally put into space, and it's just really amazing how people smarter than me were able to build this and put it in space, and now we get to use it. So for those of you not familiar with telescopes, there's maybe two big questions. As why do we want to put telescopes in space when it's so expensive and we have the Earth, right? And the other one, why do we always want bigger telescopes? Because every telescope we make is bigger than the previous one. Even on Earth, we have the very large telescope, and then the next one is the extremely large telescope, and after that, who knows, right? The ginormous telescope or something like that. So why do we want to put it in space? It's just basically because we can go around the problem of having an atmosphere. Because at Earth, we have an atmosphere, which means that we can't observe some sorts of radiation. We can't observe UV radiation, for example, from Earth, because our atmosphere just blocks it out. But even if you're observing other wavelengths, and I'm going to go into that in the next slide with wavelengths, you always have issues with atmosphere because you have turbulence, you have clouds, you have all sort of stuff happening. So it's always nicer to have something in space. I'm actually really hoping we build something in the moon at some point, because that would be really, really cool. On the other side, why do we need them to be bigger and bigger? And I put an I in this slide because it's the same way our people? I'm not a native. So it's the same way our people works, in the sense that if it's dark and we need to collect more light, the people gets larger, right? And it's because we just need to collect more light in order to see things. So, yes?
What's the benefit of putting a telescope on the moon as opposed to the atmosphere, as opposed to like in space?
Well, the moon would be stationary, and you could be sending people up there all the time to fix it if something happens, whereas like the James Webb, the Hubble was closer in orbit, so you could still get people to go and fix things when they break. The JWST, if it breaks, it breaks. We can't go and fix it. So having a stationary base in the moon would be really, really ideal. And yeah, the bigger the better, because you get to collect more light. And the more light you collect, the further away you can see. The further away you can see in distance means the further away in time you're seeing. So you're seeing the early universe. And for some reason, that's just what we want. We want to see as much as we can and as early as we can to understand what the universe is about. So the James Webb Telescope is an infrared telescope. So this is just going to be a very quick reminder of what that means. So the light is an electromagnetic wave. This is just visible light. I'm sure you're all familiar with Pink Floyd and the prism breaking the light into different colors. So basically what I care about this slide is that the different colors just mean that the light has different wavelengths. And in astronomy, we always talk about red and blue. We like red being long, blue being short. That's just the way we see things. However, the visible spectrum is not the entire picture. Light has a full spectrum of a huge spectrum, and we only see that tiny piece there is visible. So the James Webb is not observing visible light, it's observing infrared light, which means wavelengths longer than the red. So it's a bit like what Predator sees, if you watch Predator. Now, what does that mean in real terms for us using the telescope? We take advantage of an effect that's called redshift, and it's because the universe, as it expands, the galaxies that are further away are moving away from us. Everything is moving away from us, basically. And that produces a redshift. So as the fabric of space and time stretches, so does the spectrum of light. So something that was optical in our first image, the same galaxy, if it's further away, it gets stretched. So something that was optical turns suddenly into infrared wavelengths, and we can see it with the James Webb. So another figure showing the same thing, this is from one of NASA's animations. If you look at one galaxy and you assume the same galaxy is just moved further away, you're going to see that it goes from being blue, the same galaxy now far away just looks red. That's it. So what does that mean in terms of James Webb? Is that very nearby to us, we can unveil mysteries that we can't with the visible because we're seeing the infrared. So, Predator, of course. It was really hard to find a cat dressed as Predator. This was the best I could do. But then far away in the early universe, we can see optical features of galaxies because we're basically seeing the optical light that got redshifted. So it gives us unprecedented views of the universe. As a comparison to other facilities, this figure is a bit old, as you can see, because James Webb was a future instrument, but I corrected it very subtly. So we have ground-based observatories that can see early so far. Here in the bottom we have the Big Bang would be here, and then how many years from the Big Bang we could see. And as instruments got better and better, we can see closer and closer to the Big Bang. So in particular here, it's highlighted the Hubble instrument and James Webb. The reason the Hubble is more than once is that when we call deep fields, and you will see this in every instrument in astronomy, what we mean is that we pointed it in one direction for a really long time. So you got more light, and it's a deep field. The same way that a camera works if you leave your exposure for longer, it's the same thing. So how do they compare, and why can the JWST see so much further than Hubble? One of the big reasons is just the size of the mirrors. So this is just a comparison, side by side, of how big the mirrors are. Now in terms of early universe, this is a bit of the same figure basically. And we have that the Hubble can see when the modern galaxies have formed, so galaxies that are closer to us. However, the JWST can see beyond that, can can see beyond when the galaxies were formed, it can see when the first stars were formed. This has never been seen before. I cannot stress this enough. We have never been able to see the first stars. And now there are papers claiming that we are seeing indeed the first stars, and it's amazing. Chile astronomers are nerds. The brightest, furthest away star is named after a lot of the rings thing. It's an envy. Yes?
Is that limit of how far we can go back? Because before there were stars, there's nothing
Yes.
to see. So it feels like we're close to that
Yes.
limit.
Yes, indeed, you're right. So our limit would be the age of the observable universe, because the light can only travel at a certain speed. So we can observe about 14 billion years into the past, which is really close.
So has anybody estimated how big the telescope would need to be in order to go right?
I'm not sure. I'm actually not very good at telescopes. I know there's plans to launch a new space one very much like the James Webb, but optical, but that one is like twice the size. So I think if we went with the James Webb that was twice the size, we could go a bit further, but it's probably not necessary. I think if we do deep enough images with James Webb, we can get what we're looking for. And we are finding things that maybe we didn't know we were looking for, so that's cool. So here just a little comparison between Hubble Deep Field and the JWST of the same field. There's thousands of galaxies here. So that was Hubble, JWST, Hubble, JWST. So you see that much more things appear in the JWST, specifically the red ones. And those red ones, as I was saying, it just means they're really far away. They're very early galaxies, all these red dots that appear that Hubble just couldn't see because it wasn't seeing deep enough. And if you're curious of how big a size that is in the sky, because if you see the moon, you know it's like a thumb, right, in the sky in size. This is 1 grain of sand placed at arm's length, and that's what you see. In 1 grain of sand at arm's length. The universe is so full of things, and it's so cool. So, yeah, it's really exciting. So now that we're fully equipped to understand what James Webb does, I'm going to show you some very beautiful pictures of things that are close to us and what we can learn from them. So the first one, the pillars of creation, maybe you've seen this before. This is from the Eagle Nebula, which is inside our Milky Way, so it's the same galaxy. On the left we have optical pictures from Hubble, and you can see there's very dark regions where it's dusty and very dense, so you can't see through them. But then in James Webb, since it's infrared, it shows us the invisible things that we couldn't see. It shows us the predator eyes. And so we can see stars where we didn't see them before. So stellar evolution, in general, is pretty well understood. We have a very good idea of how and where stars form. However, how that actually happens and seeing it as it happens is necessary in order to really understand what's going on. So stars, just a very brief overview. Stars are formed in regions where there's a lot of gas and a lot of dust, because you need that gas to at some point start collapsing because of gravity, and you get a star eventually because the pressure is so big that you start igniting hydrogen and then you get a star. So we know this happens in these regions, especially where it's darker, but now we can see it specifically in this finger here. All these little dots that appear there are stars that are hidden within the dust because they're young stars. And then the tips that look really red over there, that's just a very cold region. So maybe I should go through this now because we're going to see this in every picture. These are not real pictures in the sense that it's not the colors that you would see, especially with James Webb because it's infrared. So what we do is that we combine different filters. And in every image you're going to see, the scale is not the same. So blue here doesn't mean the same as blue here. However, within an image, blue means harder, shorter wavelengths. redder means colder, longer wavelengths. So here as well, I don't know if it's easy to see in the projection, but around the fingers, there's like a light blue diffuse component going on. That's gas that's being heated by the stars around it. And so that's why also the red means just really cold molecular dust where stars are being born. Now another thing that we can look at is the phantom galaxy, which has a really cool name. I don't know why. It's a phantom galaxy. This is optical, this is Webb infrared. So in the optical, in this side, the red dots is the spiral arms of the galaxy, so very much like the Milky Way, it's got spiral arms. And the red dots is where the stars are being formed. It's where they're being born. And the center, it just looks like a diffuse blob. That's where the older stars are. Now, when we look at the same with infrared, what we're looking at is at the dust and the gas. So you see that the dust and the gas is in the arms where the stars are being formed. And you see concentrations here where the stars are being formed as well. For my research, even though I look at early galaxies, what is really interesting about this one is you get these holes, like that one there. So these holes where there's no gas and no dust. And that's because of stars, when they die, if they're massive enough, they'll be supernovae, and they just explode and they blow channels, they blow away the gas and dust around it. And that to me is really interesting. So here you get to see in action how it happens, because in the early galaxies you will never get an image this pretty. You just see a blob. And the center that looks really blue is the warmer component. And it's all these older stars that here we couldn't see because we didn't have enough resolution. Here, if you zoom the image enough, you would see its individual blue points. It's just a lot of old stars that are in the center of this galaxy. This one here is a planetary nebula, which astronomers like to name things in complicated ways. It has nothing to do with planets. It's just called a planetary nebula. It's what's going to happen to the sun. It's what happens to stars that are lower mass. So the sun is a low mass star when they die. So these kind of stars don't die dramatically in a supernova, in a black hole or something like that. They just eventually grow into a red giant and they just blow off the layers very elegantly. And this is what happens here. And if you just see it in the optical, this is optical, you would be fooled to think that that bright star in the middle is responsible for this. But it is not. You can see next to that bright dot, there's a little one to the left. That's a white dwarf. That is what remains after a star, just like the sun, removes its layers. And this is what is left behind. And we can only see it because James Webb can look past some things. I think this might be my final nearby. Okay, this one's really cool. I don't know if you've ever seen it. It's called the Stephan's Quintet. It's a group of galaxies that are nearby enough that we can really study them. It's a misnomer because actually this blue one is much closer to us. So it's not part of the same group, but it's just posing there. And we only let it be and we put it in the name. But these ones around are at the same distance, and not only are they at the same distance, they are merging. So they're getting together and they're going to form, eventually, they're going to all crash together and form a big elliptical galaxy, which is the same that's going to happen to us someday when we crash with Andromeda. So this is what's happening here. The top one has a supermassive black hole that's accreting. And what's interesting about the James Webb view of this is that you can see the dust. So we see tidal waves. We see some tidal movement here. There's little tails that come out because the galaxies are merging. But we also see this full cloud of dust here that's between them. And the reason that's there is because they're merging so quickly. These two are already merging, but they're crashing into that big one so quickly that they're producing a shock front because they're just going so quick. And in that shock front, they're producing this like agglomeration of gas and dust. And as we saw in the pillars of creation, that's where stars are being born. So why is this interesting to us as astronomers? Understanding how when mergers of galaxies and interactions of galaxies trigger star formation, why do they trigger them, how do they trigger them? And at the same time, that big one over there has a supermassive black hole, so that's been studied separately as well. So it's a really cool lab to study these things. Now, I'm sorry to say there's no more pretty pictures. But we're going to go through the early universe and a bit of the drama that surrounds it. Well, you don't have to kick me out. Not done yet. So, a bit of history. We have Edwin Hubble, which I'm sure many of you have seen and have heard about him, and the Hubble law. So he basically discovered that when looking at galaxies, that the distance of the galaxy relates to how quickly the galaxy is moving away from us. So this is just the redshift that I was talking earlier. And he found that this was very proportional and it was a constant, which has been refined with new measurements, but to a first order, he was pretty spot on with his theory. And then later, Lemaitre, a Belgian priest, he took this and went a step further and tried to understand, well, if everything is, the further away it's moving quicker, then maybe it came from the same point. Everything was very close, and then it started expanding, and this is why we see this effect. So he was the first proposer of what we know now as the Big Bang. He didn't call it that, but yes. And this is a bit of a side gossip. But when he wrote his theory, he went to Einstein because he knew him. They were in a picture together, so they must have been best friends. And he showed him his calculations, and Einstein famously told him, "Your maths are correct, but your physics are abominable." It turned out to be wrong. The first person to prove him wrong. So that was just a little side piece of gossip. So knowing these things about Hubble and the Big Bang, I want to get to something that I've been seeing a lot. Ever since the James Webb came out, there's so many articles saying there's a crisis here, the astronomers are panicking, no one can sleep at night because it's all broken and we can't deal with it anymore. So I just want to go briefly through the biggest two crises that are out there, and then we can discuss if they're actually that big of a crisis. So the first one is the Hubble tension. So this is just a measurement of the Hubble constant that Edwin Hubble was doing. The big tension about this, the plot is a bit, don't pay much attention to it, but it's basically that if you measure the constant, which as a constant, it should be constant, right? So it shouldn't matter what you're using to measure it because it's a constant, right? But the problem is that when you measure it in close by galaxies using stars as your standard candles, you get one result. And when you use CMB measurements, CMB guy, anyone knows, you get a different result. So there's been a bit of a tension in people trying to understand, is it just that the Hubble constant is not a constant? So that's why at close to us it's something, at early universe it was something different. Maybe it's just something that evolves with the universe. And the other one is our distance measurements wrong. This was especially for the star part, not the CMB part. So it was proposed that maybe we're just looking at the brighter stars and this is why our measurements are wrong. And so the JWST has been used, there's a specific program in order to study these same stars and evaluate if this is the issue or not. The results are not entirely out yet. However, there are preliminary results that agree, and just this problem keeps being a problem that we don't really understand. So we either need other independent measures of the distance to galaxies to understand this, or we need to update our theories about what's going on. And then the other one, I don't know if you saw these things, but I saw them everywhere. So this was, okay, I don't want to badmouth anyone, but the Big Bang didn't happen. So this person wrote a paper 10 years ago that was called The Big Bang Didn't Happen. And then when the James Webb results came out, they were like, there's a reason the Big Bang didn't happen, and they just went with it. And then there were a bunch of other things like this, we were wrong, everything we knew was wrong, cosmology is broken, James Webb is breaking everything. And so, what do we do about it? So, to answer this, we first have to understand how do we make conclusions as astronomers. We basically we get our conclusions based on two things. We have observations, we have lots of cats observing things, many observatories, and then on the other side we have simulations, and I show some pictures here. The simulations just means that we have very, very impressive computers that can simulate the universe. So they start at a very early universe, they plug in certain physics, certain assumptions, and then they let it roll, like they let it evolve until it gets to the present age. And then they kind of compare, does it look like what the universe actually looks like or not? And there's many different ways to do this, so this is just a summary that I found on the internet. And so this is how we do our things. And so what we expected based on all of this, until now, was that when we have spiral galaxies, much as the Milky Way, which is a big, massive spiral galaxy, or Andromeda galaxy, we expected them, when they were younger, to be firstly less numerous, but also to be less defined. So if you had a very early universe spiral galaxy, we expected it to have arms that were not that defined. It was not so easy to see. You wouldn't have like a bar in the middle, just because it takes time for all these processes to settle down enough and to get this shape. So you can tell a lot from morphology. And so this was what we expected based on simulations. And when we observed close by, this seemed to be at least the case. These are galaxies that are very close with Hubble, and you can see a very defined shape, specifically that bar that forms in the middle that takes quite a while to form. And it also means that the galaxy hasn't had many interactions, so it's not like crashing around with other galaxies. So it's just been left alone for a while, and it gets to evolve and we get this. So this was great. However, what happened with JWST is that we observed things like this at a much earlier universe. So we did not expect this. So we didn't expect to see a galaxy 11 million years, is it billion years ago, that had a bar and stuff. This doesn't look as pretty as the ones before because they're so far away, so they just look a bit like blobs, but you can still see the structure. We also didn't expect that when looking into the early universe we would find so much diversity, because we always kind of expected to find these tiny blobs that were just not very massive because it was really early universe. And now suddenly we find that there are spiral galaxies, some of them have bars, and it's just not what we expected. Does that mean that cosmology is broken and that the Big Bang is wrong and that everything we know is wrong? No, it doesn't. So is there a crisis in cosmology? Yes. Yes, and you will hear about the Hubble tension, and you will also hear about this. And you will see articles about everything breaking. But basically what it means is that JWST isn't breaking anything. It's just showing us things that we didn't know. Our models and our simulations were constrained by observations. And until a year ago, we didn't have observations of the early universe, not like this. So of course all our models were calibrated to that. We need to update how we understand galaxy formation. We don't know how galaxies form so quickly in such an early universe and get this shape. We don't know, but we will learn. But nothing is broken, and the Big Bang still happened. I'm sorry to disappoint. And now reaching the end, I wanted to show you an image. The oldest, well, youngest galaxy, the most far away galaxy we've ever observed until now is this one. So just if you wanted to see it, as we go further and further, things get less pretty. But this is the most distant galaxy, well, these two, the most distant galaxies we know of. So, I'm getting to my conclusions. So we went through a couple of things. So JWST, it's an infrared space telescope. Yes?
How much do we know about, like, this first universe, galaxies, how much do we know about them? Like, do we have an idea of, like, their historical formation rates, or, like, yeah, how much information do we have?
So, for some of them, when we have near spec as well, so when we have spectroscopic information, because these are just images. When you have spectra, you can see which elements are in the galaxy and what kind of abundances we have. I think from everything I've seen in the team, the low metallicity galaxies that are pretty young. When it comes to star formation, it seems to depend a bit. Like, I'm working at JWST, and I have a sample of galaxies that seems to be brighter and more efficient in forming stars than other galaxies. So I think it's something we still are investigating. So yeah, going to my almost final slide, if there's no more questions. JWST, if you have to remember anything, it's in space. It's got a shiny gold mirror, infrared predator eyes. The second is we have our beautiful backyard. If you ever want to see those images, they are real. The only fake part of them is the coloring, but they are real. It is the universe. It's beautiful. And we can learn so much about them because we get to see the details that, as you saw at the early universe, we don't get those details. We get blobs. So it's really cool to have all this information so we can make all our conclusions. And then the early universe and the drama. There is a crisis. There are things we don't understand. That doesn't mean everything is broken. We're not lost in space. It's just something we have to update and understand better. So if any of you are interested in going to astrophysics, this is a problem that we need to solve. And what's next? Well, with JWST, we still have another good 10 years on it. So the way this works with astronomy is that we write proposals, we send them to the observatory, all of us, like every astronomer that wants to apply for this instrument, writes a proposal with the galaxies, sends it out, then there's a team that decides, and then you get time or not to observe your things. So there's so many cool programs that are going to come out of it. Hopefully one of my own, if it gets accepted. The next big telescope in space that is being kind of planned is the Carl Sagan Observatory. This would be like the James Webb, but twice in size in mirrors. And it's going to be optical, and I think the main mission of that one is to look for life. I didn't even touch the subject of life here, because I don't care. But if anyone cares, there's that. Yeah, without further ado, more cats. Thank you. Yes?
Okay, so I'm going to try to explain this from my brain on how it's going to go. But, so I get that James Webb, like, the way that light travels, we're looking into the past.
Yeah.
And it's like James Webb gets further and further out into the universe. If we were to point the camera at the same spot we did, a week after it launched, would we see changes in the picture as time has progressed, quote unquote?
Okay. So that's a good question. I think I wasn't clear enough. So James Webb isn't traveling like into space, just out there infinitely. It's orbiting the sun.
Okay.
So that orbit isn't enough to make a difference to what we see. If you were sending something into deep space, like just maybe at some point it would make a difference, but I think it would I don't think it would be feasible to get the images at that point, so it would be really far away. Sorry.
Could you hand over speakers?
Hello, thank you. Is this working? Maybe I can.
Batteries.
I'll just
Just scream at me.
Yeah. So I was curious to know about that these spiral arms, bars, whatever things that show that galaxies have got structure earlier. Okay, so models haven't accounted for them. But what sorts of things do the models need to account for them? Is it more dissipative processes that are allowed to bleed away energy so that things can fall in without angular momentum throwing them back out again? What sorts of things could allow structure to form earlier than...
You see what you said sounded great to me. It's really not my area. I'm not really sure. Like some people propose it would be a difference in the matter that you assume, like the cosmology that you assume. So there's an issue about cold matter and dark matter and warm dark matter and stuff like that. So that could be one thing. I think the spiral arms are formed through density waves. I think it's the most coherent theory. So anything that would affect density waves, I'm sure. But yeah, I'm sorry, I can't give you a better.
So there's two different values for the Hubble constant. What's the significance? I mean, does it mean that the universe, it means the universe is expanding at a different rate, but does it continue expanding under both values, or is it going to collapse under one?
Not to my knowledge. I think that they should both be expanding universes. It's a slightly different value, and to be honest, as someone who doesn't work on it, it doesn't feel like it's that huge of a difference. It's like 10, it's a factor of 10 or something.
Okay.
Yeah.
Thank you, Charlotte. It was a great talk. Dogs would have been better, but never mind. I think I might have a really stupid question, but I can't answer it myself. So you say there's this, you talk about seeing the first stars, and then saying at a particular time you kind of hit, if you go back far enough, you hit the dark ages as far as that. But if you just had a bigger telescope, or a telescope that could detect different electromagnetic radiation given the redshifts that goes on, might you just not be yet seeing the first stars? So does that make any sense? It kind of made sense in my brain before I said it.
How do you know? I was with you to almost the very end. The part of the stars confused me, because there is a physical, an actual limitation to what we can see, because after that it's just basically so early that everything was just a soup that no light could get out. So that's where we get the furthest we could see would be the CMB radiation,
So I
which
guess
is...
my question is, how do you know that?
Oh, that's a bit philosophical, no? So we know the CMB is there because we see it. It's a cosmic microwave radiation that is all over the universe, and it's uniform. So we believe that's from when the atoms finally formed, so the universe became transparent, and we see that. That would be a hard limit of how back we can go, and that's observable.
But I have heard that in theory, you could because neutrinos weren't limited by the.
Yeah, neutrinos are different. That's not visible light there, right?
We observe neutrinos with our current measurement devices.
Yeah, no, neutrinos are a different kind of worms, right? It's not just light that you're seeing in a telescope.
Hi, thank you for the talk again. I wanted to ask about dust. Like, is that a sort of constant thing that obstructs our observations, or do we need to take into account different levels of it, maybe when sort of making telescopes? And if so, how do we account for that in
Yeah.
telescopes?
Oh, that's a good question. We usually, I'm more used to galaxies because that's what I observe. And so you observe whatever came out, right? You don't know a priori if that has dust or not because it's not a constant. Not every galaxy has the same amount of dust and the same amount of gas. They're all different. So you just observe whatever came out. And then based on some traces, for example, this is going into a bit more technical, but if you have certain emission lines, like if you have H beta, H alpha, which are different recombination lines of hydrogen, the ratio between those is very sensitive to the amount of dust. So if you have those observations, you can reconstruct and be like, oh, okay, this has this amount of gas, of dust. So now you take all your observations and you correct them for that dust that you think it has. So I'm dealing with this in my current work. It's highly uncertain, especially at the early universe. So there's a lot of assumptions you have to make, and I've discovered the best you can do is just be very honest about your assumptions because we don't really know exactly how it behaves.
Hi, just a quick question. Why gold mirror?
I remember reading this just for this question. It's very reflective. It's very reflective. It's the mirrors are not entirely made of gold. It's just the coating that they have. It's a very fine coating. It's thinner than a hair. So it's just a little bit of gold, and it just helps it be much more reflective.
A basic question, when we talk about the age of the universe, we say it's 14 billion years old or something. How do we measure that? Because, I mean, if time is relative, right, depending on the reference frame, so is this a figure because we're in the Earth's reference frame, or how do we measure the exact age? Does that make sense?
Yeah, maybe the exact age. I don't know. That's why you get like 14 billion and not like 14 billion and one, right? But I think based on observational constraints, we know where the CMB is. So that's one big constraint. And then I guess the rest is a bit of just theory, is it? Do you know, Inigo?
Also, you're talking about activity, I guess. Yes, I mean, there's a preferred reference frame, which is that in which the CMB looks the same. It has no dipole. So yeah, that's the one we use to talk about it. The reference frame, which the universe looks isotropically, can look the same in every direction.
Thank you.
Sorry, this is not really a question, but more of a comment. You seem to be concerned a little bit about reporting on things. And I thought you might actually, when we turned on the Large Hadron Collider, a lot of us had to go out and work. And a colleague of mine from Oxford went out and joined us as we sort of like fiddled around on the day to try and make it work. And then when he went back, got to his house and tried to open his door, he had difficulty back in Oxford opening the door. Eventually he pushed it open and he found about sort of 20 newspapers had all been pushed through his door by other people in his housing estate who said, "Alan, this headline says you've told us that we're all going to self-combust." The headline was like, "Oxford scientist says humans will self-combust."
Did he say it? Did he say it?
He'd been interviewed by someone, and that's what the Oxford newspaper wrote it up. So you're not alone as well.
We'll maybe take one or two more questions and then we can go to the group.
I have a very simple question from a non-scientist. You said a phrase that really struck me. When the universe became transparent.
Aha! Yes, yes.
Explain that?
Yeah, yes, I'm sorry, that's not obvious at all. It just means that before that, there was a soup that I was mentioning. So protons and everything just, so light couldn't, even if there was light, it couldn't travel much because every time light tried to travel through the medium, there were so many things going off that they would just scatter around and never get out. And at some point when the atoms started forming, then there was order to the universe. So now you had atoms instead of having all these things going around. And so when you have atoms instead, light has channels where it can go through. So that's what I mean.
Okay, and I guess we'll... Oh yeah, thank you very much again for a very interesting talks, and thank you very much for cats, which I fed with dogs. Yeah, we can all head off to the public room now, and there's more wine and snacks, and you can ask more questions. Thank you very much.
To my wallpaper.
Come on.
Okay, I'm gonna end the stream. Thank you for coming.